Hello physics students, this is Dr. Brenzy here. We are on lesson 3.1.7 and today's topic is going to be potential energy diagrams. In our last lesson we learned about conservative forces, and conservative forces are those that conserve the total energy in an object. And one of the properties of conservative forces is that we can assign a potential energy function along a path. So at a given position x, the gravitational potential energy is equal to m times g times x. We already figured that out. So if we were to plot the gravitational potential energy versus a displacement, then we would get a linear function like this. What's neat about these potential energy diagrams is that you can actually calculate the force by taking the derivative of the potential energy with respect to x. And when we do that with our potential energy from gravity, we get negative d over dx times mgx, and our force due to gravity is equal to negative mg. Now that's what we already know. But we can do this with any gravitational potential in general. It doesn't need to be just the gravitational force. So that's one cool thing about finding about potential energy, is that you can take the derivative of potential energy with respect to distance or displacement, and take the opposite sign of that, and you will get the force of that potential energy. So if you're looking at a graph of u of g versus x, well, the derivative is the slope at any given moment. So the slope of the tangent line. Well, we don't have a tangent line here because this is linear, so the force is going to be the opposite of the slope of this line. So if you're looking at this, the slope of this line is actually equal to mg. The force from this potential energy will be the opposite of that, which is negative fg, or negative mg, So one thing is that about conservative forces is that they always are pushing the object toward a lower potential energy. So if I have an object way out here, and it has this potential energy right here, I know that when it's at this, actually I shouldn't say at this potential energy, but if it's at this position right here, at this position x, which we commonly think of as the height, then the force is going to push it toward a lower x, toward a lower potential energy. So just by looking at a potential energy diagram and looking at the slope, I can automatically say which direction the force is going to point. So because my lower potential energies are over in this direction, over here, I can automatically say, well, the force is going to be pointing in this direction, and I don't even need to do any calculations. So any object in a conserved system, in other words, a system that has no non-conservative forces, the total energy of that system is going to be a horizontal line, because in a conserved system, this energy, this total energy, which is kinetic plus potential, does not change. It stays constant, no matter where I am. So what's interesting about this is if I know that my object is at a certain distance or displacement right here, x, I can automatically see that if it has this total energy up here, that the kinetic energy has to be the difference between this line and that point right there. So I can automatically figure out that this amount is the kinetic energy, and this amount right here has to be potential energy. And I can get that just by looking at this diagram. Another neat feature about potential energy diagrams is that an object with this particular energy can only be in a place where the total energy is greater than the potential energy. If that's not the case, then in order to get total energy, then my kinetic energy would have to be negative, and that's impossible. So I can look at a potential energy diagram, and if I know my total energy of my particle or my object, then I know that it has to be somewhere between this displacement right here and that displacement right there. So I know that it has a maximum displacement x. Now, how does that work? What are we thinking of when we think of gravitational energy here, or gravitational force, is that this is the maximum height that the object can travel up to if it has this much total energy. Now with spring potential energy, we have a different function. We have a spring potential that's equal to 1/2 kx squared. So instead of making a line like we do with gravitation, or gravity, excuse me, the spring force has a parabolic potential energy function. So if we have an object that is moving on a spring, and it has a total amount of energy E right here, which is kinetic plus potential, then it is going to move, it's going to have to be somewhere between here and here. Another interesting thing about this is that if we were to do negative work to take some energy out of this system, let's say its new energy would be right here, after we've done some work to take energy out of the system with a non-conservative force. And then if we take that non-conservative force away, well, its new total energy is going to be down here. So what happened is after I took some energy away, it's no longer able to go out to this large of a stretch or a compression, but it has to get closer and closer to 0 right here. So what does that look like on a spring? Well, up here with this amount of energy, we have a spring that is getting compressed a lot. Actually, why don't I put that on the other side? Oops. So here we have a spring that's being compressed a lot because the displacement is large and negative. So let's draw a spring that, well, that doesn't look good enough. Here we go. We have a spring that is really compressed. And over here, since the displacement is large and positive, we can think of this as a spring that is really, really stretched out. Okay, like that. So what happens after we take some energy out of the system here? Well, it can't compress nearly as far as this one did up here, and it can't nearly stretch as far as this one did up here. So it's getting closer and closer to what it would look like if it had no stretch at all. Okay, and if we were to take all of the energy out of the system, then it is going to rest at a point x equals 0. And that's like that's where the spring is neither compressed nor stretched. Now let's look at the spring force. So when you have a potential energy diagram that's a parabola, if we take the derivative of 1/2 kx squared, we get k times x. And then if we take the opposite of that, our force, our spring force, is equal to negative kx. Well, we're familiar with that, right? So what does that mean? That means that when the farther and farther I get away from 0, the larger and larger the force is going to be in the opposite direction. Okay. I could also look at my slope, the slope of my potential energy function, and realize that when I have a really large instantaneous slope, I also have a very large force going toward lower potential energy. So here I have a large negative force. Over here, actually I should say over here, I have a large positive force because the instantaneous slope at this point is large and negative. When I get down here, my potential energy is 0, and not only is it 0, but the instantaneous slope at that point is 0, so that means that the force is also equal to 0 at this point. So when I have a particle here, an object on a spring, and it has this much total energy, all of this energy at this point is going to be kinetic, right? In other words, at this moment, this particle is either moving to the left or to the right. And it's moving to the left or to the right with a lot of kinetic energy. And at this instantaneous moment, there is no force acting on the particle at all. So it is going to continue its motion. So what's going to happen, let's say I was coming from the left and going to the right, I'm going to continue through this point. There's nothing stopping or slowing down my object on the spring at this point, so it's going to keep on going. But as it keeps on going, the kinetic energy gets smaller and smaller until it hits this point here, and then the kinetic energy is 0, so it has stopped at this point. Now, is it going to stay here? The answer is no, because I have a large negative force being applied to it. So once it stops, it's going to turn around, go this way, and it's going to keep on getting more and more speed because it's getting more and more kinetic energy. Until it gets here, the force is 0. It has a lot of kinetic energy, so it's going to want to keep on going. And it's going to keep on going until it runs out of kinetic energy. And it comes to a stop at this point. Well, is it going to stay here? No, because there is a large positive force. So it is going to turn around and it is going to start, and it's going to do the same thing over and over and over and over and over. All right, you get the picture now. So when you have a mass on a spring with a total amount of energy that's greater than 0, you're going to get something that just goes back and forth and back and forth. You're going to get an oscillation like a sine wave, back and forth. So our potential energy diagram can tell us something about the motion of a mass that has this much total energy, as long as we recognize that it has to stay between here and here, because the total energy cannot be greater than the potential energy. And we also recognize that the slope of the energy, or the potential energy, gives us the force, and that force is always pointing in the direction opposite or toward lower potential energy, opposite the slope. So if the slope is negative, the force is going to be pointing positive. So when I know about the force, and I know about where the particle can stay, and I know about the particle's kinetic energy, which is the difference between total energy and potential energy, I can get an idea of how this mass on a spring is moving. Now this is we don't know what sort of force is producing this type of potential energy graph, but let's take a look at it anyway. It looks like it has several places where the derivative du dx is equal to 0. Those are points where the instantaneous slope is 0. And remember that I told you that the force that produces this potential energy graph is equal to negative du dx. So there are particular points where the force is equal to 0. And in order to find where force is equal to 0, let's find where the slope is 0. Well, we have, looks like we have a point up here. Looks like we have a point down here. Looks like we have a point here and a point there, and all four of those points are places where the force is equal to 0. So that means if I have a particle that has exactly this much total energy, then it is going to stay exactly at this position. There's no force being applied to it. It has no kinetic energy if the total energy is equal to the potential. So it is actually going to stay here. Now, what would happen if for some reason it gained just a little bit of kinetic energy? Okay, and we gave it a little nudge in toward the right. Well, what would happen is that the force is going to, since this slope is negative, the force is going to start off with a small positive value. Remember, our force is always pushing it toward a lower potential energy. But as I go a little bit further over, what's going to happen is that force is going to get greater and greater, and here it's just going to be huge until it gets down to here, where the force is going to equal 0. Okay. So if I were to take this, if I were to take a point that has exactly this much energy and at this position, then yeah, it could stay here, but if I give it a little bit of a nudge, then it's not going to be able to stay there, and it's going to actually fall off and move to a different position. So because of that, see, I have to find a button here. Let's see, where's my erase? Looking for my eraser. Right. So this is what we would call an equilibrium point. Okay, and equilibrium just means that the force is equal to 0. So everywhere on a potential energy diagram where the slope is equal to 0, you have an equilibrium point. But this one up here, because, well, I'm just going to say it's unstable. And it's unstable because if I were to give it a little bit of a nudge, or if it were at a slightly different position than this exact position right here, then it would actually end up leaving that equilibrium point and it couldn't actually stay there. It's almost like having a marble like on top of a bowling ball. So you could actually find an exact point where a marble could balance on top of a bowling ball, but if you don't get it exactly right, that marble is just going to start to roll off the bowling ball, and you're going to have a very hard time finding that exact position where the force on the marble is pointing exactly straight down so that it can stay in that exact same place. Well, let's compare that to down here, where again we have our force equal to 0. So this is another equilibrium point, which means that the forces are all balanced, force equals 0. But if I were to nudge this one a little bit to the right, what would happen is that the force would be pointing in the opposite direction, so it would push my mass back to the equilibrium point. Likewise, if I went over to the left, my force is going to push me back over to the right. So my force is going to restore the original position of my mass or my particle or whatever is on the end of the spring. So this would be considered a stable equilibrium point. Okay? And then we could go and we could label these others. Now, because this one is a maximum, it is an unstable equilibrium point. Because as I get a little bit farther, if I push a little bit away from this point, the force is going to get greater and greater in this direction, and it's going to fall off in it, so to speak. This one is stable down here, because when I leave that position, go a little bit to the left or a little bit to the right, the force is going to restore it back to its original position. Okay, so that was a lot to digest about potential energy diagrams. I hope you find them useful. I know that they're a completely different way to look at things, but we're going to have an opportunity to practice looking at potential energy diagrams in class, and I'll look forward to seeing you then. Bye.